Okay, so what does absolute value mean?
When
Positive values.
It makes positive values. Okay, so whether we have the absolute value of positive 2 or the absolute value of negative 2,
It's 2.
it's 2. Because what is the definition of absolute value? Right?
How far it is from 0?
The distance from 0. Okay, and is a distance ever negative? No. All right. Now, when we think of absolute value in terms of a function, if you didn't know how to graph any function, what you would probably do is pick values for your input, pick values for x, and see what you get out for your y. So if I picked negative 3, what's the absolute value of negative 3?
3.
3. The absolute value of negative 2?
2.
The absolute value of negative 1?
1.
0?
0.
1?
1.
2?
2.
3?
3.
Okay, let's plot them. Negative 3, 3. Negative 2, 2. Negative 1, 1. 0, 0. 1, 1. 2, 2. 3, 3. Absolute value makes a function that looks a lot like a v.
That is a V. Can we just call them V functions?
It's the victorious function.
Victoria's Secret.
I knew that was coming.
Yeah.
Sometimes you just totally reaffirm the fact that I teach 9th grade boys. Okay?
She's fine with that. It's about as good.
And 10th grade boys.
Alright.
Alright, domain. Is
Game.
there any restriction? Is there any restriction on our input?
No.
No. It goes from negative infinity to positive infinity. There's no restriction. All reals. Okay, our range for this particular absolute value function, it goes from 0 to infinity. And y equals the absolute value of x is our parent graph for an absolute value function. No transformations have occurred with this. No shifting, no reflecting, no stretching. And so when there's absolutely no transformations, it's our parent graph. Now, absolute value, just like a quadratic, is symmetric across a vertical line. So it has an axis of symmetry, and this axis of symmetry is the vertical line x equals 0. That is the y-axis. All right, this function increases from here to forever. So it has an increasing interval from 0 to infinity, and it decreases from here to forever. So negative infinity to 0, it is decreasing. We can also describe the end behavior of this function, and with every absolute value, both ends are going to do the same thing. As x approaches positive or negative infinity, in this graph, y approaches positive infinity. There are other things we can talk about this function. We can talk about the y-intercept, 0, 0. We can talk about the x-intercept, 0, 0. They're the same. Every absolute value will have a y-intercept. It may or may not have an x-intercept. All right, so this is the sheet you picked up when you came in. So we're going to do 1, 5, and 6 together. We're going to talk about those characteristics here in class. Your homework is slightly different from what was originally on the calendar. We have changed the calendar. Your homework is to finish whatever problems we don't do in class today on what you picked up. So if you had printed out the other calendar, the book work, we're going to do for a warm-up Monday. So don't worry about any book work. Yeah. So whatever we do not finish in class today, so I'm picking some, going through them, and then you get the rest. Okay? Front and back.
Are we gonna have time in the class?
We should, but my technical glitch gave us time to socialize ahead of this.
Alright.
And so we probably won't have that time after. All right, we know all about transformations, guys. How is this function transformed?
Right 3 up 2.
Right 3 up 2. Right 3 up 2. So that is where the vertex of this absolute value. And then it's the same moves. The absolute value of 1 is 1. The absolute value of negative 1 is 1. The absolute value of 2 is 2. The absolute value of negative 2 is 2. So if I go right 1, up 1, right 2, up 2, left 1, up 1, left 2, up 2. If I went left 3, I'd go up 3. Right 3, up 3. Those are the absolute values of those moves. So this is that function. That is how it looks. And we can always describe the domain of any function. This one is not restricted. It's everything. What is the range of this particular function?
2 to infinity.
2 to infinity. This one has an axis of symmetry. X equals what?
2. No, 3.
3. Okay, x equals 3 right here is our axis of symmetry. Okay, this function is increasing. It increases on this side. As you go right, it goes up. That's increasing. So it increases from that x value of 3 at the vertex to infinity. This function decreases from negative infinity up to 3. So this is where this function goes downhill. Shoop. That's the decreasing interval. And we can describe the end behavior as x approaches, and since the ends are the same, we're going to take a shortcut, positive or negative infinity. Y approaches what?
Infinity.
Infinity. Okay. Number 5. Number 5. Where does the vertex get shifted to for number 5? Up 4. Okay, now the negative out in front of the absolute value. What does it cause it to do? Go down, that's right. Flip upside down. If we were to state it in words, we would say this is a reflection. It's a reflection over the x-axis, which causes it to open down. So our same moves, except we're doing the opposite of all of them, so that it opens down.
It's crazy, bro.
Okay, the domain remains unchanged. But this time the range is different. Because this one opens down, range is always the least y value to the greatest y value, and it goes down forever. So the way we describe that is negative infinity. Up to the greatest y value, what is the greatest y value of this function? 4. Okay, the axis of symmetry is a vertical line that passes through that vertex, so it would be x equals, and what is the x value here at the vertex? 0. X equals 0, once again, is the equation for the y-axis. All right, increasing, decreasing. So these are going to be different because this one was reflected. This function is increasing here. So this function is, as we move right, is increasing on this side. So from negative infinity to 0. And this function decreases from that point on. So it's decreasing from 0 to positive infinity. It was hard to see my negative. Let me try that again. Negative infinity. There we go. Let's do the end behavior as x approaches positive or negative infinity. What is this function approaching?
Negative infinity.
It sure is. Now, we could give x-intercepts if asked. We could give the y-intercept if asked. Because it's a function, we can refer to these x-intercepts as our zeros of the function. Okay, number 6. Take a look at number 6. How is it shifted?
Right 4.
Right 4. Now, number 6 has a vertical stretch. So instead of 1, 1, 2, 2, we're going to go 1, 3, 2, 6. That's it. Now, those of you that remember doing absolute value, why would we do it again? How does this fit into what we're doing now? Do you see that each of these functions could be described by 2 rays? So we could rewrite any of these absolute value functions as piecewise functions.
That's nice.
Yeah, it could be written either way. So that's what we'll do in just a moment. How many of you, raise your hand, do remember doing this before?
Not with functions.
Okay. All right, the range of this one would be from 0 to infinity. Where is the axis of symmetry?
X equals 4.
X equals 4. Great. This one is increasing over the interval from 4 to infinity. And it is decreasing from negative infinity up to 4. Now, in behavior, as x approaches positive or negative infinity, this function approaches positive infinity. Okay, so for homework, you got 2, 3, and 4. Easy cheesy.
That's it?
Well,
You
on
thought.
okay. So, The next section asks us to write both an absolute value equation and then a piecewise. Now, I'm going to show you 2 different ways to do this. The first, we're going to start with the absolute value every time because that's our new one for today. So take a look at this one. Let's see if we can account for any reflections, any stretch or compressions,
Bless you.
any shifting that's going on. So let's see, what do you think this is? Let's count.
The
Up
stretch
2
of 2.
over 1, up 2 over 1. Good. There's a 2, a vertical stretch of 2. Now, there's no shift left or right, so we don't need anything added to our x, but this vertex goes down to -6.
Just wait.
It's a little tricky.
3, 4, 5.
Minus 6.
Oh.
Yeah.
Alright, minus 5.
Go to the tape. Now. What do you do? I'll
All right, so let's jump to this one and let's see if we can do an absolute value for this one. Now, this one's going to open down, so we know it has to be negative, right? So let's do a slope. 1, 2, 3, 4 over 1, 2, 3. 4/3. So 4/3 is our vertical stretch. The slope, as you go from the vertex towards positive infinity for the x value, the slope is your vertical stretch or compression. All right, the x value got moved left 1, so we put a +1 here, and it was moved up 4.
Now what did like added?
Okay, so you try writing the absolute value function for this last one. It's the easiest one. I don't usually do that. I usually give you a hard you try. Okay, did you get y equals the absolute value of x minus 2 plus 3?
Yes.
Okay, now I'm going to show you 2 different ways to write the piecewise function. We already know one. If we're given the graph, it's easy to write the piecewise function. We do one piece at a time, so we could attack the left side and then the right side. So if we were to write a linear equation that represents this side, the slope is down 2 over 1, and the y-intercept is -6. Now that's for x values that are less than or equal to 0. Or you could use the inequality notation here from -infinity to 0. And then the right side is up 2 over 1, up 2 over 1. So it's positive 2x minus 6. And that's for x values that are greater than 0. Now you can choose where your equal to goes. It can go here or here, but not both. Okay, now how could I have done that if you couldn't see the graph? So let's say it wasn't there, and all you had was this. Okay, to do the left side, you just do the opposite slope. Okay, so this is 2. To do the left side, I would do the opposite slope, -2. And then take your absolute value and treat them like parentheses. To do the right side, you do the same slope. So if I take this and I just distribute that 2, that's the right side. Is that exactly what I got here?
Yes.
Yes. So left side, you do the opposite slope. Right side, you do the same. Now, it's really simple on one like this, whose vertex lives right there at the origin, on the y-axis. So let's see how that same thing plays out here. It's very helpful here because this slope is -4/3. So if I continue that up 4/3, I see that this crosses at a funky spot. It's not an integer. So having those rules kind of help me out here. So for the left side, I would do the opposite of the slope. For the right side, I would do the same slope. Now this can be simplified. We can distribute and combine like terms. All right, here's a warning for all of you that are working on your homework on the other side. Nowhere will you find this explained again. And so you're missing this explanation. You might want to go back and watch the video later because I will ask you to do this without a graph. Okay, so here we're going to distribute, and what we get is 4/3 x plus 4/3 plus 4. So this is f of x equals 4/3 x plus, this is 1 1/3, so that would be 5 1/3. Does it look like it kind of crosses a little bit above 5? Yeah. And so that's for x values that are less than or equal to, what is the x value right there? -1. Now this one is also going to be something that you wouldn't be able to eyeball, but you can algebraically find it out. So this is 4 minus 1 1/3. So 4 minus 1 1/3 would be 2 2/3. Does it look like this part crosses right here about 2 2/3? Yeah. So we figured out exactly doing it algebraically, which we couldn't have done graphically. Okay, so you try number 9. Write the piecewise function. You can do it graphically, you can do it algebraically. That one works both ways. Yeah. Anytime I give you one like number 8, where the y-intercept is not an integer, you have to be able to do it out. If we were to write this as a piecewise function to describe the left side, it's pretty simple. We can see it. It's a negative x is my slope, and I can count my y-intercept. 1, 2, 3, 4, 5. Now, if I did it algebraically, I would get exactly the same thing. So if I did the opposite here, instead of an understood +1, it'd be an understood -1 out in front. So we get negative x plus 2 plus 3, same thing. That's the left side. So the left side changes to the opposite, and that's for x values that are less than or equal to, what is this x value here? 2. The right side, you keep the same slope, so it's like a +1. So this becomes x minus 2 plus 3. That would tell me the y-intercept would be 1. If I kept this going, is the y-intercept 1? Yes. So this one works graphically. It also works algebraically. This is for x values that are greater than 2. Okay, so I'm going to erase our work here, because I'm sure you have that written down. And then I'm going to move the, whoa, no, I want to move the writing. Oh, wrong. There we go. And we'll slide this back up in here. We'll slide it. Things just really aren't working out for me right now. I've had technical glitches all day long. There we go. Did it. Okay. Now we're going to look at two ways to solve absolute value equations. The first method I'm going to show you is the algebraic method, and the reason why is because this is what you're going to see on the SAT and the ACT. Now, our standards, our Common Core standards, don't ask me to teach you the algebraic way, but that's silly, because that would just open up the door for you to miss that one on the SAT and ACT, and it's not covered anyplace else in the curriculum. So we're going to do it now, okay? So algebraically, and then we're going to check by looking at our graphs. How many of you noticed that the equation we came up with here is the same as that? And the equation we came up here is the same as that. And the equation we came up right here is the same as that. So what that means is we can use these graphs to help us check our work algebraically. Did that on purpose. Okay, so let's take a look at the first one. Algebraically, whenever we solve an equation, we need to isolate our variable. Well, when the variable happens to be inside the absolute value bars, that means we have to isolate the absolute value. So, we got to get rid of everything else. Got to move your 6. And then you divide by 2. Now, this is possible. It is possible for an absolute value to equal a positive number. What if I got right here and it said the absolute value equals -3? Nope. There would be no solutions because that is not possible. So that's the first thing you want to check. Is it possible? Yes, it is. Now, what that means is that everything within the absolute value bars either has to equal +3, because the absolute value of +3 is 3, or -3. So we take everything inside the absolute value bars, set it equal to the positive, and set it equal to the negative. Well, in this equation, I'm done. That's all I needed to do. There's nothing else to do to solve. So what are my two solutions? 3 or -3. Now, how can I verify that algebraically? If I go, this says where does that equal 0? So if I come right here where it's 0 and draw a line, do you see it intersects right here at -3 and right there at +3? Graphically, algebraically. Okay, let's do number 8 together. I have to isolate the absolute value. So I get -4/3, absolute value of x plus 1 equals -4. Luckily, for this problem, when I multiply by the reciprocal right here, this is now going to become a positive value. So it is actually possible. So I get the absolute value of x plus 1 equals 3. Now, it doesn't always equal 3. I don't know why I did that. Okay, so what that means is all of this stuff either equals +3 or all of this stuff equals -3. So this is where we have to split it. X plus 1 equals +3, or x plus 1 could equal -3. Either way, that would end up being true. So if I solve this one, I get x equals 2, or solve this one, I get -4. Now, if I came back and checked it, we want to know where it equals 0. So once again, y equals 0. Now, what is this value? -4. What is that value? +2. it right. So if I plug in -4, I get a true statement. If I plug in 2, I get a true statement. Okay, that one's for you. Okay, do the same thing. Isolate your absolute value, split the 2, and solve. Check by looking at your graph. Okay, so we'll save that one for homework. Last one we're going to do together. This is number 10 at the bottom. Now, we can also solve these algebraically or graphically. Now, if we do it graphically, this part is what you think of as your function. Y equals the absolute value of x plus 1 minus 4. So I'm going left 1, down 4, and then normal moves. Draw in my V. Oops. Undo. Selected the wrong arrow. That one. That way. And then that way. Okay, so if we did it graphically, it's going to be right here and right here where it crosses. That's where it equals 0. But this says where is it less than or equal to 0? All the way from here to here. It is less than or equal to 0. So this one is actually less than or equal to 0 from -5 to +3. Alright, so now let's solve this same inequality, algebraically. So we get the absolute value of x plus 1 is less than or equal to 4. We have isolated the absolute value. Alright, so what we would do, the two possibilities are 4 or -4, right? So 4, everything kind of stays the same. But if I do the -4, what happens when I introduce a negative to an inequality when it wasn't there before? You have to flip the inequality.
That's right.
So when we do the opposite of this, we have to flip the inequality. Okay, so here we get x is less than or equal to 3. Here we get x is greater than or equal to -5. Well, if it's less than 3 and greater than -5, isn't that interval?
Yep.
Yeah. We could actually write it as a compound inequality. All the answers are between -5 and 3. That's what these two together mean. So here they are as separate inequalities. This is as a compound, and that is as an interval. Now, what happens if you start working on an absolute value, and you get right here, and it says absolute value of x plus 3 is less than or equal to -5. Is it possible for an absolute value to be negative?
No.
No.
No solution.
No solution. Okay, so don't just get and rote step 1, step 2, step 3, step. Think about it before you start solving it, because sometimes that can save you some time. If you see an absolute value and you see a negative, think about it. Now, what about this? The absolute value of everything is greater than -5, isn't it?
Yeah.
So it would go from no solutions to all real solutions, which we could describe as the interval from -infinity to +infinity, couldn't we? Okay, so this one, no solution if we flipped it around. So you just kind of have to think about it. All right, so the rest of the front is yours. We did most of it, honestly. And then the back is review. So you ought to be able to finish this up. You actually, it's quick. It's not that painful.
No, it's not painful.
Afterwards.
I wanna sit here.
Alright.
Alright. Wait, this is.
At least you finished.
This was a